Hello everyone, we are FlexiLink. Our team has four members, me, Tuấn Đạt, a hardware developer, Minh Hiếu, các bạn are computer vision programmer, and Tất Đạt, a video editor. We're all from Ho Chi Minh University of Technology. Today, four of us would like to talk about the developing process of our remote control car using AI and gestures. When our team received the car from the organization committee, first of all, we recognized that the car wasn't perfect in design. The vehicle's machinery and internal components are easily damages because they don't have anything to cover. That's why we immediately start making the car sale. As you can see, our team has designed a car shell with former panels based on the shape of real-life truck. On the one hand, there are two major drawbacks when designing a shell for a car. Firstly, our team had to fill the gap between the car and the shell and turn the car into a square shape. Due to the distance, the car is not slim and not easy to squeeze through the narrow gaps as before. Secondly, to guarantee the hardness for the shell, we have to use the 3mm promise panels. This may weaken the transmission signal from our car to the computer and also relays in control and video quality, but not too hard. On the other hand, our team believes that the benefits are more significant than such disadvantages. For reason, one reason for this view is that the truck is more attractive thanks to the outer shell. We can easily decorate it with black paint and sticker. Secondly, the shell is quite hard and can reduce its external impact for the vehicle machinery and internal components. Last but not least, during the designing process, our team realized that the car's center of gravity is quite high and the car may overturn when having impact from the side. That's why we lower the position on the bar and have the car steadier.
About software, I created a website that interacts with our model. On the website, there are three boxes with different functions. The first box is used to establish a connection between the website and the model. In first step, we need to connect to the microbit device by using the web Bluetooth API. Through this Bluetooth connection, the web sends information about Wi-Fi and mode to the microbit. After the microbit has this information is sent to Raspberry. Both of the Raspberry and the website will set up a WebSocket to communicate with each other. This is necessary for real-time data exchange, which is important to many features like streaming video and device control. Video data is encoded by video decoder and efficiently transmitted over these WebSocket connections, ensuring a smooth video streaming experience with low delay. In the second box, I used HTML canvas to display video capture from the user's computer webcam. Set to the webcam is complete by the Media Device API. The webcam is used to recognize hand gestures through the media by library, which processes data using computer vision models. This information is sent to the Raspberry and further transmitted to the microbit for controlling model via the mod server. So, in simple terms, my website can show video from camera and understand hand movement to control model.
Based on the instructions in training session, Artem decided to use Google MediaPy framework to create a customized gesture recognition model. MediaPy Marker, an integral of the MediaPy framework, is built on a strong foundation of TensorFlow. By leveraging TensorFlow capabilities in gesture learning, we were able to meet our specific requirements, ensure that our model could adapt to our unique purpose. The model takes the raw image as input. uses hand detection to crop hand from the image, detect the hand landmark, and create an embedding vector of gesture and predict the hand gesture. The behind mechanism is uses a very deep neural network. This neuron begins with input layers, then move through convolution layers to extract features. Uses residual block for handling depth, include pulling layers to reduce dimension, and trial layer to limit overfitting, and wastefully connected layers for making predictions. Attack the pre-trained models output layers as an input layers and incorporate additional layers to tailor my model. As a result of using transfer learning, our primary responsibility was to focus on data collection and selecting suitable hyperparameters. When it comes to data collection, we made a choice not to rely on existing internet dataset. Instead, we employ CP2 and CP zone hand tracking model to detect hands and capture images at predefined intervals. We capture approximately 200 images for each layers, totaling around 1,400 pictures. This approach allows us to create a dataset tailored precisely to our needs. And here is some data examples. For model training, we found Google Colab to be the ideal solution. Since we started with a pre-trained model, our main task was to customize the model's output for specific gesture recognition tasks. First, we push the dataset in a GitHub and download into the Colab. And here is on the gesture we have. Our dataset was divided into 3 sets: 80% for training, 10% for validation, and 10% for testing. Additionally, we carefully fine-tune hyperparameters to train the model effectively. And for the evaluation, the validation accuracy can reach 89%. That shows us a strength and convenience of using pre-trained model. Following successful training, we made a trained model available for download. We hosted it in GitHub, providing a direct link for downloading. Then we simply replaced the link in the sample code by our model link. The model exhibited an impressive accuracy rate up to 86%, highlighting its effectiveness in recognizing gestures. Here is the demonstration of my model.